Hello everyone and good evening. Welcome to the final session of this beginner track with Explore ML. And today we're going to be talking something about problem frame. But before we get into what we'll be talking about and all the things that we'll be dealing with, let's have a quick revision. So what is supervised machine learning? So supervised machine learning model is that model where during the training phase, you're giving the model labeled data. So you can take this example as if we want a model to classify between the color red and the color blue, we already give this model data where we as the programmers, we know that we're giving it a red color data and we know we're giving it a blue color data. So we know what we want the model to predict in the end. Can someone tell me what unsupervised machine learning is?
The model recognizes patterns in the unlabeled data so that it can classify them into different types.
Correct, that's absolutely right. And that's actually a very perfect definition for unsupervised learning. And does anyone know any algorithm or a very common algorithm associated with unsupervised learning? So when you usually try to find pattern between unlabeled data, what do you do when you find a feature of similarity? What do you do to that data when you find something that's similar?
I categorize it as one class.
Yes, exactly. So categorizing it as one class. So categorizing as in you can also call it grouping. And when you can also call it grouping, can you also call it clustering? So that's what you're doing. Whatever data you have, wherever you find similarities in this unlabeled data, you cluster it together in one group. So the algorithm or very common algorithm for unsupervised learning is known as clustering. So let's get started with today's session. So today, first, we're going to learn some very important jargon that's associated with machine learning. Now, you may ask, why do we need to learn jargon? Because as you progress on the path of machine learning, you're going to come across these terms so many times. People are going to use only these terms and not going to be explaining it to you in layman terms. So when you take up a project or do anything as such, it is important that you know the jargon that's associated with that domain. It doesn't have to be machine learning. If you're interested in web or app or any other domain as well, it is very important for you to know the jargon that's associated with that domain as well. All right. So let's get started with the first word or first terminology that we'll be learning. That is called label. So if you can see the equation that's there on screen, this is the equation for linear regression. Now, we briefly touched upon linear regression in the previous session. So does anyone remember what linear regression is and what it does? Or can anyone tell me what regression is? Just regression in general.
Giving a value or
Yeah.
looking quality.
Yeah, correct. So the output of a machine learning model, if it is a value, then that problem is regression. If the output is basically you classifying something into two different classes, like you want the model to predict whether it's a dog or a cat, that is two different classes, right? Dog is one class and a cat is another class. So that is known as a classification problem. Now, linear regression. What is linear regression? So suppose you have a set of data points, or let's just imagine in your head, you have data points, and on the x-axis, you have, let's say, the number of hours a student studies. And on the y-axis, let's say you have the number of marks the person scores. So based on this, you have certain data points on a graph. Now, what do you need to do? You need to train a machine learning model in such a way that given the number of hours a student studies, you want to predict the number of marks that student may get. So this is a regression problem because you're giving in a feature and what you're trying to do, you're trying to predict an output as a number. So that's why it's called regression. Now, since it's in a graph with this x and y axis, the easiest machine learning model you can apply to this is linear regression. So what do you do in linear regression? You basically try to fit a straight line through all the points that are there in that particular graph. So you try to fit a straight line in such a way that it accurately or tries to accurately model all the data points. So that is known as linear regression. And if you look carefully at this resembles the equation of a line. So maybe in your class 11 or 12, you may have learned that the equation for a line is y equals to mx plus c. So don't you think this also looks similar to that? So this is linear regression. What do you do in linear regression? Basically, you try to fit a line through the data points that you have. So here, label is always referred to the value that we're predicting. So this is the equation for linear regression. And in linear regression, y or the label or the value that we're predicting is a number. So if you go back to my previous example, I said that you have the number of hours a student studies. Given this data, you want to predict the number of marks that student scores. So here, label or the thing that we're predicting is what? Can someone tell me that? In this example, what is the value that we're predicting?
Why?
Sorry?
Why?
Yes, y. So what does y represent in this example? So I'll just repeat my example. Let's say you have basically the number of hours a student studies and the number of marks the students obtains, and you want to predict the number of marks the students obtains. So here y represents
Marks.
correct, exactly. So y here represents the number of marks that the student obtains because that's what you're predicting. Similarly, if you go back to our classification example where you want to train a model to classify whether it's a cat or a dog, then what is the label in that case? What are you predicting? So the label in that case would be either a cat or a dog because that's what you're predicting, right? So always remember that any machine learning model, the value that you're predicting is called a label. It could be either classification problem or regression or any other type of problem. All right, now let's talk about features. We actually spoke a little bit about features in the previous class. So does anyone remember what features are?
Features are like the main properties.
Correct, exactly. So features are the properties that is associated with a particular object. So that's what features are. And if you see in this equation, we understood that this y is the label, while this x1, x2, so on and so forth are the features. So if you take this simple equation of the problem that I just gave you, which is given the number of hours a student studies, you want to predict the number of marks the student gets. So you already know that the number of marks the student gets is modeled as y over here. So here x1 or the feature that we're giving the model or the property that we want to give the model to help it predict the output. That is what a feature is, right? That's the input variable. So the input variable here would be what? In this example, if the label is the number of hours a person is studying, then the input variable will be
X1, X2.
yes. So what does x1 and x2 or x1 in this case stand for? Because we just have one feature for this example. No problem. So x1 here will stand for the number of hours the student studies. So the problem is just this. You have the number of hours the student studies and you want to predict how many marks that student scores. So the feature or the input that you're giving to the model, that will be the number of hours the student studies, and that will be x1. So we have more than one feature that you want to differentiate. Suppose you have the number of hours the student studies and whether the student takes notes or not. Then that means that you have two features. So that means x1 will represent one feature, which could be the number of hours the student studies, and x2 will represent another feature, which is whether that student takes notes or not. So x1, x2 and so on, there can be as many features as you want. So these x1, x2 and so forth are features of the model, or what you can say is input to the model, using these properties, you'll be able to predict an output. So that's what features are. Next, we have an example. So example is called a particular instance of the data x. Now this may sound confusing, but it's actually very simple. So if you have, let's say, again, let's go back to the previous problem. Now you have the number of hours a student studies, you have the data of whether a student takes notes or not, and you want to predict the number of marks the student scores. So what this whole data, that is the number of hours the student studies, whether the student takes notes or not, and the predicting variable y, which is the number of marks, excluding the predicting variable y, just the two features, that is the number of hours the student studies and whether the student takes notes or not. That is considered to be the example or a particular instance of the data. So like I mentioned, features are what is fed as input to the data. So features can be many. Now all of these features combined together, they form the example. So there could be many examples, right? So you could have, for student 1, they study for 6 hours and they don't take notes. Maybe student 2 studies for 8 hours and they do take notes. So the student 1, that is 6 hours and does not take notes. That is one example. Then example 2 will be student 2 who studies for 8 hours and does take notes. So these two features, that is the number of hours the student studies and whether the student takes notes or not, combined together give you the example or a particular instance of that data. Now, labeled example. So once again, where are labeled examples used? Or labeled data, if I should say. What type of machine learning model is it used in?
Supervised.
Exactly, correct. So labeled examples or labeled data is used in supervised machine learning models. And as is mentioned here, it is simply used to train the model. So you have features and labels. So when you give a feature and a label, so how will you give a feature and a label? So what was the feature from the previous example? Can anyone just repeat? What were the features that we were using in this running example?
Number of
X1, X2.
student studies and does he takes notes or not?
Correct. And I think Abhishek also mentioned X1, X2. That is absolutely correct. I just wanted to know the elaboration of the names of the features. So that is the number of hours the student studies as well as whether the student takes notes or not. So these together form an example. Now a labeled example is that example where you're also adding the label. So when you're training a supervised machine learning model, you will always give the data along with an example. So the example was what, like Amog mentioned, you have the number of hours the student studies as well as whether the student takes notes or not. Then a labeled example would be the number of hours the number of marks the student gets. See, the number of marks the student gets is what we're trying to predict in this example, right? So that is the label associated with it. And when we're training a supervised model, we always give in a label. That is why a labeled example always has all the features along with the value we want to predict, that is the label. And this is only used during training. So this is only used in the phase of training where we're giving unsupervised model labeled examples and we're telling this unsupervised machine learning model to learn from it. When we're testing the model, we only give it an example. We don't give it a labeled example. When we're testing the model, we will only be giving the number of hours the person studies and whether the person takes notes or not. Using this information, the machine learning model will have to predict the number of marks the person gets. But other than that, when we're actually using this data to train, that time we also attach the label to it, which is the number of marks the student gets, and that is known as a labeled example. So hope the terminology so far are clear. So label is the value that we're predicting. Features basically are the input to a machine learning model, which have basically properties or patterns that the machine learning model must understand and learn to predict its final answer. Now, example is a particular data instance. So you can think of it as a combination of all the features at one particular moment. So for like one particular row, you can think of it as like if you look at an Excel, for each student, for one student, they will have one entry for the number of hours they studied and one entry for whether they took notes or not. So this one entry, each entry is known as a separate example. So yeah, that is what an example is called. Labeled example is all the features taken along with the label in one entry. So if you have again the number of hours the student studies, whether the student takes notes or not, along with the marks the student gets, that's a labeled example and that's used for training. All right, moving on. An unlabeled example. So this, as you all mentioned, is used in unsupervised machine learning models. And what is this? We're giving unlabeled examples to the data and the data has to learn from it. So that is an unsupervised machine learning model where we're giving unlabeled examples and the model has to learn from it. But where else is unlabeled example used? Apart from using it for unsupervised machine learning model, where else is an unlabeled example used? It is also used when you're testing a machine learning model. No matter what type of machine learning model it is, we always give in unlabeled examples to the machine learning model during the testing phase. So this unlabeled example is what will help the model predict based on the data and give you an output. So again, when we're testing this current example that we have running, we will only be giving the number of hours the person studies and whether the person takes notes or not. So that is an unlabeled example because we're omitting the label. All right. Okay, a model. What is a model? So, like I mentioned, always think of this model as a black box that does the task that you want it to do. So, what does a model do? It maps the examples to the prediction labels. So now example, this is the example you're given. So in our current example, like our current scenario, what is an example? What is the example that we're using for our current scenario? The whole student, number of hours, whether it takes notes or not, and marks. What is the example here?
Number of hours and if he takes notes or not.
Correct, exactly. That is absolutely right. So what does this model do? It basically takes these examples that, as Amog rightly said, the number of hours a student studies, as well as whether the student takes takes notes or not, and using this data, it tries to predict the label. The label here is the marks that the student obtains. So that's what a model does. A machine learning model can be of various types. It could be supervised learning model, unsupervised, or any other type. But the main job of this model is to take the examples and help you get the predicted label. Okay, so that, and it is defined by internal parameters which are learned. So when the model is getting trained on its data, like we've mentioned in all these sessions, a machine learning model is one that learns on its own from the data. We don't specifically program any rules for this, right? So when it learns from this data, it has it understands certain patterns and other internal parameters using which it can map the examples to the prediction. So that's what a model does. It basically, given the examples that you have, it tries to give you the prediction or the output label, which is in our case the marks a student obtains. Okay, now I'll give it over to Nikhilesh, who will be continuing the rest of the session.
So, hello everyone. I'm Nikhilesh. So, let's just revise quickly about some of the major things that Sneha has covered. So, some of the major things were like label, feature, example, and other related keywords like model, unbiased, unlabeled examples, labeled examples, and related information. So, right now, let's see the keywords in action like in a particular objective. So from here on, let's have like interactive session where I would be asking you some kind of some examples related to machine learning, and let's figure out what can be the labels, features, examples, and etc. So let's what can be the label, feature, and other keyword for this particular example, like deep learning algorithm does as well as dermatologist in identifying skin cancer. So based on what you have understood in previous session, can anyone give us information about what can be the label, like what can be the label with respect to skin cancer? Our objective is to find skin cancer. So what can be the labels here? So I'll just give you one head start with this example. So in this, label can be classification of like cancer or no cancer, or to be very specific, the model can even identify type of cancer like malignant cancer or non-malignant cancer. So very specific cancer also it can find. So the label can be cancer or no cancer or a specific cancer too. So that can be the label here. So it comes under classification and other stuff. So what can be the feature, like what can be the features to f- to predict this label or whether cancer should be or not? Like for skin cancer, what are the key factors which affect the decision of the model? Like what can be the input for this uh, model?
Patient diagnosis detail.
Mm-hmm. Can you come again, Amog?
Patient diagnosis detail. What are the details we have about the patient that can be the feature?
Yes, like can you come little specific? Like, can you come little in depth? Like what can be the feature here? Like when you see cancer, like okay, I'll give you an example. So here we have skin cancer, right? So skin cancer is more of visual feature. So you have like the size or the color or the time frame in which it has increased from different sizes. So there are different factors, right? So visual factors, then even based on some clinical factors, like some values from clinical reports. So it's like, the size of it, then the borders of the cancer, if a cancer is an irregular shape, and every factor depends. So in this particular scenario, it is a visual feature. So let's talk about like example. So here example can be a visual skin cancer patch where you can clearly observe it, and machine learning models can find out which kind of cancer it can be. So that is an example for this. And what can be the labeled examples? So we know that example is like visual or like any clinical reports. So what are the labeled examples here? So here the labeled cancer can be like from radiologist. If an image is being classified as an particular type of cancer, then that is called labeled example. If it is not labeled like a particular cancer, then it is unlabeled. It's very easy. So if it is labeled by a radiologist for a particular type of cancer, it is labeled. Otherwise, it's unlabeled. So what can be the output here? So like you input the labels, you input like different examples, like images and everything. So what are you expecting out of the skin cancer machine learning model?
Is it a skin cancer or not?
Yes, that's correct. So we should never forget our objective. So let's see another example. So now the task is little different, but it is interesting. Image recognition in the smart camera task. In If you have observed this particular task in like it, or a module inside the Google Crowdsource, you would have experienced like it's classifying different object detection in like for different objects. So can anyone say how many types of labels can that be in that for that particular model here, like smart camera task?
N number of labels.
Yes, it can be n number of labels, but there is a finite. So there is a limit, but for this particular smart camera task, it's a very huge list, but there are finite number. So yes. So what can be the features for this example? What can be the features for this example? Okay, so for this particular feature, so what is like you can relate features to the input to the model. So what is model saying? The images, right? So the feature of this model will be the images in this particular scenario. Okay, if you look into stock market, the features for the stock market would be the stock prices. So that is like you can relate with this perspective. So in here it is an image, and what can be the example for this? What can be the examples of for this particular model?
Recognizing
Object. Yes,
each
yes, yes.
object
Correct.
and naming.
Yes. Yes, that's correct. Recognizing each object and each image is an example. So what are the labeled examples? What are unlabeled examples?
Label means like this is a bottle or this is a
Yes. Yes,
uh,
yes. Hmm.
unlabeled.
So yeah. Yeah.
Unlabeled is things which are not like we don't know thing, but there is some pattern in um, the images what you are seeing.
Correct. So, like here, you're mentioning the label, right? So they are labeled examples. But if you just give an image and you don't give a label, then they are classified under unlabeled. It's yeah, it is as easy as you understand the names of this title. So, what can be the output for this
Recognizing each object and
object?
try to
Yes,
name them.
and classifying it into different classes from that huge list of available classes. So Yes, the model predicts only the classes which it was trained on. So it can be five classes, it can be 100 classes, or it can be even 10,000 classes. So there is a finite list, but yeah, the limitation is it will only classify what it is trained on. So the examples, labeled examples, everything is very important. Okay, so in translation task, so let's see the objective of our ML application. Translating a phrase or word in translate task on the Crowdsource app. So what can be like if you have tried a translation module in Crowdsource application, what can be the label?
Language it is in.
Yes. So like the language to which it has to which it is supposed to translate is an metadata. So the difference between a label and metadata is, so you're telling model like a particular setting, so you need to train for from this text to another text. So in this particular scenario, the label is the text that you are giving. So if you are giving English, that the text that you're providing for English is the label here. So the languages that you're selecting is like you're trying to select a particular model. So it is not what you're giving to the model. So what you give to the model is the actual content, like what is the text or audio, something like that. So it's more of the content, what you want to translate, that would be the label here. So okay, so what would be the feature here in this particular scenario? Okay, so the label and features are both of them are text. So here the feature can be from which language it is supposed to be translated. So when we take example of Hindi and English, so the feature for translating Hindi to English is the feature is Hindi. So whatever you input to the model is a feature. So here we are inputting Hindi text. So that Hindi text is is the label, or like you can call it as a feature. So whatever you're predicting is the label, so that is English text. So yes, so what is an example in this particular scenario? Like where do you use this particular application example? Like I just gave an example for Hindi to English text, so what can be other examples for translation task? Okay, so the answer for this particular thing is it can be audio. So if you give Hindi audio, it should be able to translate with proper understanding to English with the same context to English audio. So that can be another example for phrase. So here we have seen word, I just gave before an example for word like text. So there can be another example like phrase, like where you're translating an audio. So what are labeled and unlabeled examples in this scenario?
You are giving the name of that particular language. For
Yes, yes, yes. No, no, no. So no, we do like okay. So there is a confusion between selecting the languages and the input to the model. So Amog, so you can think of like whenever you select a language, right? Hindi to English, you are selecting a particular model out of bunch of models. So you have like English to Hindi model, then English to French model, but out of this you need to only select Hindi to English, right? So when you give English like Hindi and English, you're selecting only that particular model. Okay, so that is like kind of, you can think of like application metadata, like that is a different thing. But here you already have a model. So you have a model which is training from, like, which is translating Hindi to English. So what is the input for this model, and what are the labeled examples for this? So for this, like, I know that this particular concept of translation is little bit tricky, but it is very simple. So here we are giving like we are getting label, and the same label you can call it as like labeled examples, and the unlabeled can be Hindi text or audio, and labeled examples can be Hindi text or audio. So that is the examples for this. And what is the output for this? So it is similar to this example. So if we take a word, then the output would be a word. If we take a phrase, then the output would be a phrase. So yes, so that is, now let's, yes, so we are done with the examples. Now let's look into scientific method of approaching a problem. Right now we have seen different keywords how we have applied, Now let's say look into how do you create an objective, like creating a task for like mission, like a voice translation or something like that. So in our scientific method approach, like you have seven different checkpoints that you need to oversee. So first is framing the problem. Then you need to make an hypothesis. We'll look into what that means later on. And the third is collect the data, test hypothesis, analyze results, reach a conclusion, and if there is a mistake, then refine and repeat the process. So first, in our example, we our first problem we have to frame is what will traffic be like tomorrow. So that is our first objective, or the framing the problem. So what is an hypothesis? Weather forecast could be informative. So that is like we are trying to achieve like, see, there is a confusion between hypothesis and a problem. So the problem is to solve what will be the traffic tomorrow. But when you look into like model specific, this is more into what kind of forecast, like whether it should be rainy or sunny, or like these kind of things you need to find out with respect to model. And based on like sunny or weather, like sunny or rainy, you need to say that, oh, tomorrow the traffic, like, it will be rainy, and you need to be like, you need to give more additional information along with the model prediction. So here our hypothesis is weather forecast would be informative. So the next is collect historical traffic and weather data. So here our traffic our traffic and weather data is correlated. Like if something changes, even like, traffic, like if weather changes, then even the traffic changes. If it is rainy, there might be more traffic. So that is one of the relation here. So then we need to collect the data, like for traffic, historical traffic and weather data. We need to create a simple model. We need to input this data and labels, and we need to test this simple model in our application. And is this model better than existing systems? If it is better, then we can replace our existing systems. If it is not, then we will change and we'll get more data, or we'll change the objective, like collecting only this data, or increase the type of data, like different patterns like user behavior or something like that. So this is our scientific approach to what will traffic be like tomorrow. So problem framing practice. So your landscaping business is hiring people, like this is a new example. So your landscaping business is hiring people for the fall season. You want to predict how many leaves will fall from a tree each day, so you hire the right number of people to clean up. So to just up the entire objective, you need to, like, you have a business, you need to find out how many leaves that in a particular season, and based on that you need to hire people. So some of the like, we need to we need to have a clear idea about all these five objectives. One is clear use case. So do we have clear use case? So the main objective is to hire people based on the number of leaves. So that is clear use case. So predict the number of leaves. So that is the use case. So next is know the problem. So the problem that you need to hire people but don't know how many people you will actually need in a given day. So the problem is you don't know how many leaves, or you don't know how many people you need in a particular scenario. So that is a problem here you're trying to solve. You need to predict number of people like required in a particular season based on the input of number of leaves. You have a lot of data, like you need to, like, the problem with this particular scenario is how effective are you able to collect number of leaves. So you know that leaves shed a lot of leaves, and is it like accurate to find a lot of data, like different trees, different locations, different scenarios. So the collecting of data is also in question whether it is going to be accurate. So the next is predictive power. Like even if you have a lot of data, like number of leaves, what if the weather is different? What if it is raining? The number of people to clean leaves during a rainy season might increase. So the predictive power of it might not be that accurate. So these are the things that you need to keep in mind before before getting into machine learning model. So the next is aim to make decisions, not just predictions. So machine learning model can do predictions. That is very easy to do, but is it worth converting those predictions to decisions? Here when you see number of leaves is very unpredictable. So even if you have even if you have predictions, you can't make decisions based on those predictions. These predictions can just be full of garbage or anything that sort. So when you're training, or like majority of engineers work on trying to solve, but rather they don't work on making a case. So in this particular situation of hiring people based on number of leaves, it is not a good decision to go with this approach. There are a lot of problems in this approach. So do anybody have any problem with respect to this problem, and why we can't make proper decisions?
Yes, yes.
Yes,
Why
yes.
we can't make the proper decision?
Okay, you have that doubt.
Yes, yes, yes.
Okay, okay. So we have number of leaves, right?
Uh,
So like we discussed here, so the model that they want to propose is you have input of like number of leaves, and you need to get number of people you need for that thing. But the problem is you can't get accurate input data. Like sometimes it might be windy and the number of leaves might change. Like the number of leaves changes with respect to season. If it is rainy, all the leaves stay on the ground, stick to the ground. So it's like the data changes with respect to season in different parts of the year and different locations. So the input to the like model, like number of leaves might change, and it might not be accurate. And and the next thing is, even if you find out the number of people you need, you can't reliably make decisions based on it. So that is one more thing that you need to keep in mind. So basically, like here, leaves to number of people, but there is other factor like climate, then different factors involving in this approach, but we were not considering before. So the next, like, aim to make decisions, not just predictions. It's like to create decisions, right? You need to have reliable predictions. In this particular scenario, it is not possible. You need to refine the problem statement, like number of leaves, the season, time, then different factors involving this, and then you can predict accurate one. So just by number of leaves, it is very unpredictable. The model can get predictions, but the decisions might get affected by these poor predictions. So is it clear, Abhishek?
yes, little bit. Okay.
Okay, if you have any doubt, or if you find little difficult to uh, understand, you can ask a specific doubt, like where you're facing a doubt, or like problem with this question.
Okay. Further, I will ask the question, but
Okay,
proceed with your slides.
okay, okay. Thank you. So okay, so the next problem is, a beekeeper wants to analyze pictures of their honeybees and identify their role within their colony, sorry, in within their colony. So anybody wants to say a clear use case here in this particular scenario, what this uh, objective wants to satisfy, or what is a clear use case?
Identify a particular type of bee. I mean, the bees in that colony, and knowing their roles.
Yes, based on their actions. Like a particular bee might do a specific action, we need to find out a specific bees based on their actions. So that is use case. So what is the problem here? The problem is identifying the bees. Okay, so the next, do we have a lot of data? It depends upon who is collecting it and where they're collecting it. So the next is predictive power. Will it be accurate? Here, if you see the
Yes,
number of, okay, okay, yeah, yeah, go on, Amok.
predicting power, it can be to a certain extent, because um, there's only like a one particular type of bee doing this work, like doing honey or the colonies extending it.
Yes, yes.
Accuracy will be there, but not as much as we expect it to be.
Yes. There might be few edge cases like there might be poor, like you, even if you have a lot of data, the data quality might be poor. Like some of the data might have not so clear, like actions are done based on the movement of these bees. So what if the collection of the data is not done clear, like properly, there might be some effect on the predictive power. So the fifth one, decisions, not just predictions. So what, like, would you consider this a good fit for an ML problem? Like this, like the problem use case, do you think that this is a good way to, 1 minute? Yes. So would you consider this particular scenario as a good fit to using machine learning?
Yes.
Yes.
Yes. Okay. It is like the predictive power might be low because of the data, but you can to find to some extent have a context about what's happening with the bees based on machine learning. Yes. So some of the issues that you can encounter in this particular scenario, what can they be? Like any issues that you face other than, like, poor quality of data or other things. Like, do you have any other issues that you might face while you're creating the machine learning model?
If we are looking into like only one type of honeycomb nearby, that could be solved like a bit more accurate. But if we are seeing number of honeycombs elsewhere or in the area, that would make be a difficult for as a
Ye-
ML problem, because
yes,
can
yes,
be a
yes,
different type of
yes.
bees also. So
Yes, that's correct, Amog. The term that is used in industry to specify this problem is called generalization. So the bees that you train on might not be the same bees that you might test it on. So, like, you need to have like diverse data sets. Like it should, like the data set should be good quality, and along with that it should be diverse. So here you get generalization issue. So that is another issue that is part of future sessions or other advanced topic. Yes, so you can remember that particular issue as a generalization issue. Yes. So let's look into another example. So the example that here we need to find out is a teacher wants to predict a student's end of year test results based on a student's performance on mini tests throughout the year. So what is a clear use case here? Like, can anybody simplify our objective?
like depending upon the performance that the person has got in the mini test, that could be like the average of it, or the maximum marks of it could be the student end of the year test result.
Yes, like yes, it is good, but we are looking into machine learning approach, so you don't calculate averages. So here the problem case, Amok, here is you have a lot of mini tests, like smaller, like 5 marks quizzes, but there the model, the objective here we need to do is 5 marks quizzes in periodical tests. Take, like, after taking the input or the data from that particular quizzes, you need to predict the end end semester exams, like 100 marks exam. So that is a clear use case. Like, you need to take collection of smaller tests and use them to predict the final test. So that is a thing. So what can, like how are we planning on solving this using machine learning? Like what type of machine learning do we use for this? Okay.
Giving a certain value for within that range.
Yes. Suppose if we take the final test is between 0 and 100, like from 0 to 100, then the, like, we try to predict the final test score between that. So the possible type of machine learning will be used is regression model. So that's what we'll use. And do you have a lot of data? Like, what are your opinions on that for this particular objective?
the number of data will be given as per the person.
Mm-hmm. Yes. So some like the problem with a lot of data is it depends upon number of students and number of smaller tests. So that is an issue with respect to data. So what is a what do you think of predictive power? Will it be reliable or what?
Number of times it is yes, but depends on the situation of the student or a person on the day of the test. If he's
Yes, yes,
absent
yes,
or he's not well or he's unable to write, anything
yes.
can be the reason.
Yes, like we have seen in previous examples, the predictive power gets affected by external factors like users. Uh, like when we train the model with the data set, we have collection of marks, only marks, but we don't have any other inputs like what the student is up to. Like sometimes because of extracurricular activities the quizzes might be affected, but the final score, like the preparation for it, might not be affected. So there are different factors involved in this which we are not taking consideration, like sometimes illness, like different factors. So the predictive power might get affected. So can we take decisions upon this? Should
No,
we take decisions based on these predictions? Why do you think that? Why we should not take decisions based on this?
like if we take decision and that is only applicable for certain number of students, but whereas it will not be applicable for all type of students.
Yes, yes, Amog. So it is not like it is not for all the people. It might be working for few people, but the model might be overfitted to only certain category of people, but it might be like completely false for other group. So that the decisions might not be accurate. So we should not create a model for all people based on just the students performance on mini test. If it is including other factors, then the question of taking decisions is questionable. So based on the number of features or different, after trial runs, if it is performing good, probably you can take partial decisions based on this. So yes. So, okay. So let's take a custom thing. Okay. Custom machine learning objective that I will create now. So here I can create any organization where that will benefit from ML model. As you know that Google has a division called Waymo. So it's self-driving car, or you can even take example as Tesla. So these both companies try to solve a particular problem of automating the driving. So anybody, like, I know that it is already in a clear use case. Let's see, like what kind of problem that these machine learning objectives are trying to solve. Anybody wants to try and guess what, like how they are trying to solve?
Like the self-driving car which you mentioned about Waymo, if it's driving in a parking lot and you know that it's taking a turn and that if a person comes in between at to a certain length from the car,
Yes.
tries to predict that is he going to cross the road or is he going to go in
Hmm.
the path or does he going to directly come in front of the car? It's going to predict that. Based upon that, it stops. Uh,
Yes. 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 That's
can
correct, Among. Yes. Like you have mentioned about an action that it might predict. It can even do like identifying objects. If it sees a pedestrian, it just needs to apply brakes. So like there are different types of problems, like vision problem, and it can be even like lidar problem. So radar and other like different kinds of data is involved in this. So the problem for this is little bit diverse and complicated, but when we look into simpler lens, like predicting the future of where the car should be or what it should be doing. So yes. So the data for like you have a lot of data. Yes. So when you look into companies like Waymo, you have a lot of data. So data such as like computer data, like computer vision data, lidar data, and different kinds of sensors, driving driver sensors, like whether the driver is sleepy or not, like different things. So the model should predict different kinds of factors, so it collects different sensors, so you have a lot of data. So
It
yes,
also
there.
wants to
Yes, yes.
know like is it to a certain area. It gets to know like okay, this is a parking lot, this is a pedestrian going, and there's a
Yes,
signal in front of me. There are this many cars, so you can predict which signal is going to come next, so that it gets prepared for the next action.
correct, correct. Yes, different signals, or you can think different, yes, different features. So different factors affecting this. So the collection also comes from diverse data. So we have a lot of data in this scenario. So what is a predictive power? To how good is the predictive power? Like, are like predictions reliable? Can it be used? Anything that sort?
Yeah, it can be used better than making human errors.
Yes,
Right
yes.
now,
Predictive power is, I can't say whether it is above human accuracy or below human accuracy, but I can say that the reliability of this particular models has nowadays come to nearly to human accuracy. So there is a lot of reliability in this particular model. And can you take decisions on it? Like, do you apply this in real world?
in certain places, that could work.
Yes, yes. Like the factors, like the answer for this is yes and no. So the answer, like why it is yes, is you can use it in particular scenarios, like data, like the data might come from, a lot of data might come from like Mumbai. So you can only deploy this model properly in Mumbai, but you can't do it in Bangalore or Hyderabad. So that is a, like you can deploy, if you're deploying in Mumbai, then the decision is yes, you can deploy with very good reliability. But if you're doing, the answer is no, for like if you're deploying at different locations which it was not trained on, which it doesn't know, like how to drive. So the decision is depends upon user, depends upon the place and the time. If it is at night, probably the model might not be that accurate, because it would have not seen a lot of night data. Probably it might not be effective if it is rainy, so the vision data might be a little bit corrupted, so the decisions it took might not be that good. So there are a lot of issues around it, but to some extent it is performing better than what it was before. So yes. So yes. So a lot of machine learning models have different opinions with respect to people and on the country and different factors involved in it. So it's always good to create this kind of problem framing for each kind of any kind of machine learning model before we jump into the data, or like get into uh, nitty gritty of the problem and the model.
Thank you so much for attending our events. We'll be ending this
And
section. Thank you so much.